section 2.4 deals with solving right triangles, and it also starts to get into a couple of applications of right triangles, such as angles of elevation and depression. And then there's a weird like surveying application just stuck in here randomly. So that's kind of interesting too. So the first part of this is usually very, very easy for people, and the second part people struggle with. So you need to be very, very careful when we get into the word problems. I have to introduce you to significant digits. Okay, you're probably not going to have time to like write this down right now, but understand that it is on my website. So, you know, if you don't have time to write it all down, there's no way you'll be able to get it all. Just listen for a minute, and then you can always go back to the website and take the notes if you need to. A significant digit is a digit that is obtained by actual measurement. Okay, so if I go out and I say, you know, oh, it's somewhere between 17 and 18 feet, and I measure, you know, well, I only measured to 2 significant digits. Okay, because I said 17 and 18. So I would either write down 17 or 18, and that would not be very precise. But if I went out there and I took a ruler, you know, or a tape measure, and I measured like 17.25, that's a lot more precise. So you're dealing with precision, you know, and how far you can go and how small of an increment you've measured in. That's what significant digits are all about. Okay? Your final answer for a trig problem can only have as many significant digits as its least accurate given number. So you look at every number in the problem individually, okay? And then you decide how many significant digits that has, and you use the lowest. So like if you have one number that has 2, one number that has 3, and one number that has 5 significant digits, you use the lowest. Now sometimes because like angles are measured differently than lengths, your book will do angles on their own. They won't use, you know what I mean? Like they'll do the angles one way and they'll do the side lengths of the triangle another, a separate significant digit. I usually take it either way because physics books go back and forth that way too. So it just depends on who's teaching you. If you're in question, ask. Okay? Right angles are not used. They're considered exactly 90, because if we look at 90 by itself, it would only have one significant digit, but you don't let that count. A right angle is considered 90 point infinitely many zeros automatically. You do not use it as one of your significant digits. Always give your answer to significant digits when solving applied trig problems unless otherwise specified. Occasionally I will say rounded to the nearest tenth just to avoid any confusion. But you know, if you're not told from now on, use appropriate significant digits starting now. If you're not sure, ask. Okay? Here are the rules. Okay, I'm going to make this as easy for you as I can. Any number that is not 0 is considered significant. So that means it counts as 1, right? If it's not 0. So the ambiguity comes from 0. Which zeros get counted as a significant digit and which get ignored, okay? So any non-zero gets counted. A 0 between 2 non-zeros counts automatically. Doesn't matter if there's a decimal place or not. If the 0 is in between 2 non-zeros, it counts. Got it? All right? A 0 after a decimal is significant only if there is a non-zero number before the 0. And the last thing, a 0 at the end of a whole number is never significant. So I'll give you a minute if you want to write those rules down. So now that we understand the rules, let's look and count for these examples along the bottom. The significant digits are highlighted in blue. All 3 of these numbers, 4, 0, 8, count as significant. This is said to have 3 significant digits, the 4 and the 8 because they're not 0, and the 0 gets counted because it's in between. If it's zeros in between non-zeros, always count. Okay? This one has how many? 3 because none of them are 0. This one has 4. It's 4 because zeros after a decimal count as long as there is something before that 0 that is not a 0. Does that make sense? Okay. So here, these zeros count. But here, if you look at this one, none of these count. Because they're leading up to zeros. Okay? So there has to be something before the decimal before the 0 after a decimal that makes it count. This one would only have 2. But these count. This one has how many? 4, yeah. 6 and 7, and then because there's something before these zeros, they also count. Now this one's kind of interesting because these two zeros do not count as significant digits, but this one does because there's something before it that is. So that one's 1, 2, 3, 4. This is the one that I don't like. I never liked this one, and this is where I have trouble. 7,300 has how many?
2.
Only 2. Because zeros at the end of a whole number are never considered significant unless you put a decimal after them. Okay? I don't like that because to me, if I say 7,300, I mean 7,300. You know, like I would never be like, oh, it's about 7,300. Like that makes no sense to me. You know, I would say like, it's probably 10. I would actually measure 10, you know? So this has always bothered me, but it doesn't count. Not here, not in chemistry, and not in physics, unless
you put a decimal.
unless I put a dot after it. If I put a dot there, then all 4 count, which is weird. But right as it stands, a 0 at the end of a whole number is considered not to count. So how many significant digits does 100 have?
1.
1. All right, that has 1. How many does 101 count? Have?
3.
3. Okay, so it's
That
really
makes
weird.
sense.
I guess. I just don't like it. Okay. Any questions about that? All right. There's a big chart here, and I'm not really going to take the time to go through it, but it talks about how to deal with degrees, minutes, and seconds. Basically, you don't, just remember, you can't treat the minutes and seconds like they are decimals. You treat them just like whole numbers, okay? So like this one right here has 3. This one also has 3. This one has 4. This one also has 4. This one has how many? Does this 0 count?
No.
This one does because it's between the 1 and the 5. Okay, so it does count, but this one doesn't because it's at the very end. Okay, they're treated like whole numbers. You look at them like a big whole number there. So you have 1, 2, 3, 4, 5. So this one has 5, and that one obviously has 5. Okay? All right. That brings us up to getting ready to solve right triangles. Okay? To solve a right triangle, you can use 4 things. Okay? You can use the definitions of sine, cosine, and tangent, and that would be SOHCAHTOA. Okay? And you can use the Pythagorean theorem. Those are the 4 things you can use to solve a right triangle. If I ask you to solve a triangle, that means I want you to find all of the missing angles and all of the missing side lengths. And you can only use those 4 things to do it. Definition of sine, cosine, tangent, and the Pythagorean theorem. Okay? All right. We talked about this a little before, but I want to be very clear here. They will always label these triangles as ABC. The vertices will be capital A, B, and C. C has to be the right angle. A and B can be either one of the other angles unless you're specifically told. Okay, so it doesn't matter how you draw it. But once you put A here, big A here, you have to put side little a opposite it. So you have to have the opposite side has to have the same letter as the angle. So the little letters are for the sides, the big letters are for the angles, and little c will always be the hypotenuse. So for our first example, we would like to solve the right triangle, capital ABC, if angle A is 34 degrees and 30 minutes, and side little c is 12.7 inches. That's the interesting thing. To solve a right triangle, you only have to be given 2 pieces of information, and you can find all of the missing ones. Okay, so let's make a little diagram. Right, this is C, so this is little c. Which one do you guys want to let be A? Bottom or top? Bottom? Okay, we'll let this be A. So we'll label what we know. We know 34 degrees and 30 minutes. And we'll let this be capital B. Right? This means this is little a and this is little b. Okay. Label what you know and label what you're missing with the appropriate letter. All right. What is going to be the easiest thing to find here?
B.
I can't use B. This guy?
B. No.
Oh, big B. I forgot to mention that. You can use that to solve for the angles. What do all the angles have to add to?
You said no.
Did I? I don't think I did. They have to add to what? 180 degrees, right? So if you know two of the angles, you can find the third by just subtracting those two from 180. And that's going to be the easiest thing here, is to go ahead and just find capital B. So let's do that. We'll look for capital B has to equal 180 minus 90 minus 3430. Do y'all understand that really it's just 90 minus 3430? Yeah? Okay. So we're going to find 90 degrees minus 34 degrees and 30 minutes. Okay? Well, when I do that, I have to borrow. So really that's going to be 89 degrees and 60 minutes. Okay, so 60 minus 30 is 30, and 89 minus 34 is 55. Okay, so there's one of our answers.
I have a question. Would you change those into decimals as long as you change it back?
Okay, you can change them into decimals as long as they are exact. You can't round them because you're not allowed to round in the middle of a problem. You're only allowed to round for your final answer. Okay?
Okay.
All right. All right, so that means that capital B, that's one of our answers, is 55 degrees and 30 minutes. Does that have the appropriate number of significant digits?
Yes.
Look at the original.
Yeah.
This one has
3.
3, and this one has 3, and therefore this one should have 3. And it already does, so we don't have to do any rounding to it. So we're done with capital B. Any questions about how we found capital B and how we wrote our answer? What are the other two things I'm missing? Little a and little b. Okay. Can I use the Pythagorean theorem to find one of them right now?
No.
Why not?
Because you only have one.
You can use secretary thing.
We only have one. To use Pythagorean theorem, you have to know how many sides? 2, right. So we're going to have to use SOHCAHTOA here. Now you have to decide which one to use depending on what you know and what you want to find. So you pick. Do you want to find little a or do you want to find little b first?
Little bit.
Little b? All right, little b. Let's find little b first. If we find little b, that means I'm trying to find this side right here. Okay? I know this angle and I know this side. I need to know the relationship between those three things. It's either going to be sine, cosine, or tangent. You have to decide which one to use. And you need to work from your givens as much as possible. Try not to work from things you've already found. Work from your original diagram. Okay, is that sine? Sine would be opposite over hypotenuse, so that would be a over 12.7. I want the one that relates b and the hypotenuse, and that would be adjacent, right? So that's cosine. So that's adjacent over hypotenuse. So we will write an equation, cosine of the given angle 3430 has to equal the adjacent side, which is b, over the hypotenuse, which is 12.7. And we have to solve that. And the way you solve a SOHCAHTOA equation, unless you're looking for the angle, is you treat it like a proportion, you cross multiply, and you solve for the missing variable. So I'm going to put this over 1. I'm going to cross multiply, and that tells me that 1b equals what? Whatever, 12.7 times cosine of 3430 is. So we're going to have to put that in our calculator because that's not on our unit circle. Make sure you're in degree mode. And then what you're actually going to type in is 12.7 cosine of 34 plus 30 over what?
60.
60, yeah. Okay? Now you're going to get that answer and you're going to round it to 3 significant digits.
10.5.
10.5 what?
Inches.
Inches, okay? Now, I'm going to erase this just for a second. Give it to me unrounded.
10.44.
All the way. 10.4.
10.464026.
10.4.
664026.
That's all it gives you?
Yes, ma'am.
Okay, that's the unrounded. Well, it's technically it's still rounded, okay? All right. Now, I'm going to round it to the third significant digit, which is this guy right here. So if I round it to that guy, that goes up to 10.5, right? Did everybody get that? I didn't check it. Did everybody get that? Okay. 10.5 inches. Do you have any questions about how I came up with little b? No? Okay, let's write that down. And make sure you always put units on. Several of you lost points on your test because you didn't put degree marks. What's missing now?
A.
Little a. There are two ways we could find little a. I could go back and I could use SOHCAHTOA again and use sine,
Pythagorean theorem.
or I could use the Pythagorean theorem, okay? And I'm supposed to tell you to go back and use sine, because I'm supposed to tell you to use the given information as much as humanly possible, because that will avoid errors. When you use an answer you found, if you made a mistake on that answer and you use it to find another one, now you've made two mistakes, okay? Now, the Pythagorean theorem can be used there, but you are not allowed to use a rounded answer to find another answer. So if you choose to do the Pythagorean theorem, you have to go back to the unrounded 10.4664026 and use that in your Pythagorean theorem. And the thing about it is, I don't particularly want to type that in my calculator and square it and deal with all those decimals. I will always go back and do SOHCAHTOA again before I will deal with that. That's just me. But if you do the Pythagorean theorem here, you can't use the 10.5. You have to use this one. As many decimals as your calculator can hold before you rounded it. Because you can't use a rounded answer to find another answer. You have to use the unrounded one. I'm just going to go back and redo SOHCAHTOA. Alright, so the first time I used cosine, but to find little a, I need the opposite over the hypotenuse. Okay, so I need the sine. So I'll just work it in right here. Sine of 3430 must equal side A over 12.7. Then I will cross multiply and see that A equals 12.7 times sine of 3430. Okay, if you type that in and you round it to 3 significant digits, that will be our final answer, and we'll finally be finished with this problem.
7.1.
That's only one significant digit.
One
That's only two.
7.19.
7.19? 7.19 inches. Now that we know all of the missing things, we are finished with this problem. I'm going to stop it there because we are already way too many minutes in.